All right, let's begin. Quiet down, year 12s. Let's begin. Shh. Shh. Talk afterwards. Here we go. Let's do a bit of recap what you learned yesterday. I'm going to give you a couple of graphs, as in equations, a power function, and I want you to draw on your own exercise book what you think it may look like or what it will look like. And I want us to analyze it, okay, and think about it. And then we'll move into the last exercise for chapter 1. That's exercise 1H, applications. You're really just working with the problem, come with an equation, sketch the graph, look at the implied domain, and that's really what 1H is about. So if you got everything else, 1H is nice just to tie everything together, yeah? And then tomorrow, what I'll be doing is you can have a bit of time to do catch-ups. You know, you do your exercise 1H if you haven't gotten up to that. But I'm also giving you an assignment. It's meant to be a test, an in-class test, but given that I lost 3 sessions with you, I can't afford an sort of revision session and then an in-class test session. Will be like 2 sessions gone again. So tomorrow I'm giving you the test that is made as an assignment. You've got the weekend to do it, and then on Monday you've got to hand it back to me. Okay, now this doesn't go in your SAT. It's not anything that goes to your study score. It is just for me to know what you know, chapter 1. Yeah. So I want to be looking at. I'm not even so much interested in your answers. I'm more interested in your layout. I'm more interested in like you using the notations. How did you describe it? Are you looking at the right domain, range? Those are the things I'm looking for, and I'm hopefully going to try to fix any mistakes that you're doing. For example, if you're not describing it correctly, if you're not understanding what composite functions are, that's what the assignment's for. So when you give it back, I want full working solutions. I don't want you to just write the answer. You know, think of it as like an actual test, an actual exam. How would you lay out your answers for me as an examiner? Okay, that's what it's for. Can you? Yeah, absolutely. Yeah. Okay. So it's you giving it to me giving feedback, what you understand. Okay? All right, here we go. Predict what these graphs look like. Here we go. Y is equal to, let's do an easy one first. Let's try
X plus 2.
Let's try that one.
X to the power of 1 plus 2.
Let's try. Yeah. We'll go with those 3. Those 3. Let's recap. You look at your notes again. What are you meant to look for? Is it a fraction? Does it have asymptotes? Is it odd power, even power, negative, positive? How does it change things? I want you to predict based on what you understand so far. What could you have? What can't you have? Can I have negative values? Can I have positive values? If it's a composite function, which one exists? Which one is defined? Got it all in your head already. Pretty good. I'm not even sure myself.
That's another.
It does. Yeah, I know, right? I know.
You don't have that. No, I don't have that. In my head, it's like you go out a little.
So Mr. Tran, you're not away today, tomorrow at all? Because my only session tomorrow is and
I find it very hard to be away. In any way, even if I'm sick, it's just this coordinator role, I'm telling you, it's just every day, it's such a pain. So much work to do.
And I dropped except for this. Why did you go to the chief examiner? What? Why did you go to the chief examiner?
Chief examiner to what? I don't know what that is. Probably for special. I haven't been informed.
For like physics or something. And it's my only class.
It's too late. I got too much to do. Sorry, I'm gonna be a
I
dog.
have no what to do. Like I've got like a whole league.
I had 3 lessons that I lost. I can't lose another one.
You're right.
It's absolutely true. All right.
Do you know how many
All right, you 12s. Quiet down. Let's have a look. If we were to do the first graph, if I were to do it, I would rearrange. I don't like negative powers, so I'll rewrite this as 1 over x to the power of 1/5. X to the power of 1/5 actually just means 5th root. So technically, this is what I have. It's a 5th root of x. The first thing I already know, just by looking at that, is because it's 1 over something, it has to have asymptotes. As soon as you've got a fraction, it has to have asymptotes, because if that was 0, 1 divided by 0 is undefined. So I already know there's a vertical asymptote at x equals 0. I also know if x was infinitely large, the denominator gets much larger than 1. So that means it will approach the x-axis. And there's an asymptote there. So I already know there's 2 asymptotes just by looking at that. The second question I would ask is, well, how does the 5th root affect anything? Because if I didn't have the 5th root, it's technically just a rectangular hyperbola. So it should look like this. So how's the 5th root affected? So I look at the conditions. I say, all right, well, 5th root, can I have all values? Can I have all positive values and negative values? In our case, yes. Because it's not a square root, it's not a 4th root, it's not a 6th root, it's a 5th root. So therefore, it's an odd power. It's like saying 3rd root. You can have 3rd root of negative 27. So therefore, it means you can have 5th root of negative 27. So that means you should have both x values and both x negative and positive values. So in my head already, you've got a shape that looks like a rectangular hyperbola, okay? And I know that the 5th root only just means that it just gets smaller. It's smaller quicker. Okay, so every value, so for example, instead of 4, it would have been 1 out of 4. But now it's 1 over 5th root of 4, so it makes it even smaller. So that means all the values should skyrocket up faster because 1 over a very small value makes it larger. Okay? So that's, but overall, I should know it should look like a rectangular hyperbola. Okay? So let me show you. We can prove that. So whatever sketch you got, it should look like a rectangular hyperbola. And this is what we, actually that's negative. Oh, is that the same one I gave? No. Woo. All right. What was it again? Negative 1 over 5. There you go. See what I mean? Yeah. It's larger, but it's still going towards the x-axis eventually. Yeah, but what I said before, like when it's 4, instead of it being a quarter, 1 over 4, it's now much less than that. It just gets smaller because we're 5th rooting it, so it's larger. 1 over a very small value becomes larger value.
Just draw a quadratic.
Yeah, but when you draw it, it's just it's just a rectangular hyperbola. Okay, you don't need to draw it to scale like it's shown there, but what I want you to be able to do was to predict, because if you can predict what the graph looks like, you know the domain and range. And that's all you needed. Yeah? All right, next one. Same thing, so this one doesn't have a fraction. So I know that it doesn't have any asymptotes at this point. So I look at this and I say, all right, well, how can I break this apart? I would say I can write it as x to the power of 7 all to the power of 4th root. Or I can say it is x to the power of fourth root, or to the power of a quarter, and then all to the power of 7. One of this doesn't work. That's the one I was talking about yesterday. Which one doesn't work? Liam. Why doesn't the first one work, Athena? Why is it? Say it again. No. Yeah. It has something to do with the fraction, that quarter. Why does the first one work? Why does the second one work? Well, why not the first? This goes back to exercise 1E, composite functions. Why?
Because there's the square root of the fourth root, which means they can't be negative sides.
Fantastic. So, fourth root has a condition. Okay, so fourth root, remember that if you sub in number 2, the number 2 has to go into x to the power 7 first. So that means your machine, the first value that goes in is x to the power 7. After you work out what x to the power 7 is, you then sub that value into fourth root. Okay? So in that case there, the condition for the fourth root is that it can't square root any negative values. You can't have any negative values. Problem is, x to the power 7, you can take negative values. If I put in a negative 2 right now, negative 2 to the power 7, I don't care what it is, I just know it's going to be a negative number. As soon as I put a negative number into this, it will spit out a negative number, and that negative number goes into a fourth root. It's not going to work. So the range of x to the power 7 does not fit the domain of my second function, which is the fourth root. Yeah, range of this does not fit the domain of the second. That's exercise 1E, composite functions. Yeah. Whereas if you write it the other way around, you switch it around. This one is already implied domain that can only take positive values. When you put all positive values in, it spits out positive y values. X to the power 7 has no issues. Has no conditions. So of course it can take all values. That's why that one would make sense. But if this one makes sense, that means you already have an implied domain. You already have a restriction. The restriction is the only numbers that you can put in for the first function has to be positive. Okay, so that means I expect this new graph, x to the power 7 on 4, I expect to only have x values that are positive. I can't have any negative values. Would it make sense? Okay? So therefore, the next question is, okay, so now I know, technically, if it looks like this, is a fourth root graph, and the fourth root graph looks like this. Because it looks like your square root graph. Well, fourth root is like the square root graph. So fourth root, sixth root, eighth root, 10th root, they all follow a square root graph. Okay, that's what the even root graph looks like. Yeah, it doesn't have any negative values. If it's like cubed, third root, fifth root, seventh root, then it has the negative part, the asymmetrical look to it. Yeah, so this is my square root graph, or fourth root graph, and all I'm doing now is I'm saying take all those y values, whatever those values are, to the power 7. So if you make all these to the power 7, of course, it's going to get large. But there's one thing I told you to be careful of. Does it look like that, because it's larger now? What's it meant to look like? X to the power 7 on 4. What was the one thing I mentioned before we finished the exercise? It curves towards, instead of going towards the x-axis, because the numerator is larger than the denominator. Remember, at 4 on 4, you get a linear line. So anything above that, 5 on 4, should curve towards the y-axis. So what I should expect is it should look like this. Okay? So not like the fourth root, because the numerator is much larger. So remember, at 4 on 4, that's just a linear line. So 5 on 4 should be larger than that. And then 6 on 4, 7 on 4, and then 8 on 4 becomes quadratic. Okay? Okay, oh, sorry. So what I was trying to say, this is 1 on 1, this is x to the power 1. 5 on 4, 6 on 4 gets larger and larger, and then eventually we get to 8 on 4, so it's quadratic. 8 on 4 is 2. Okay? So, that's why, if I show you right now, once it switches, what was it again? It was 7 on 4, wasn't it? 7 on 4. There you go. It'll take a while before it goes there. 7 on 4. Okay, so no negative values, like I said. And instead of the linear line, it curves towards the y-axis. And that's what I mean by being able to read the little conditions that you have in each one. Break it apart.
Why does it, like, I understand, like, the root, But how come when it hits 2, you don't root it? Like why? Because it's also x to the power 1.5.
Yep. I know what you're trying to say.
Like why do you root that?
So, wait, let me, I know what you're asking. Are you asking this? Are you asking, why is it for this one, you get that, and this one, why isn't it like that? Is that what you're asking?
Like,
yeah?
Like, with like 1.5, like why does it, like because with whole numbers it goes up doubly, but with half numbers, like 1.5, 2.5, or 7/4, it goes up only positive, and not negative.
Oh, okay, so for
that
example,
was like 7/4.
7/4.
But it's only like
on 8/4 technically, it should be like this. So on your GeoGebra right now, if I go to 8, it will have a quadratic. That's wrong. Okay, now depends on how you say wrong, because it depends on how you write it. There's a difference between writing like that versus which actually equals to. See, these two are inherently different. Why they're inherently different is based on your condition at the start. See, the condition for this one says I can't have negatives. Over here, you remove that. Over here, you said I can take all numbers. That's why in constant functions, that's what I mean. It really matters where you put the brackets. So yes, if you simplify it, yes, it's true that it is x squared. So it has the shape of an x squared, but the domain is very different. That's similar to the example I mentioned about the uni student. It was my friend. He was doing a maths question and he asked me, and I don't do uni maths. I don't like maths at all. But I understand.
Something's not adding up here.
But when he asked this question, it's because I know the methods course really well. So because my understanding is well enough, I could tell them why it was wrong. And the question he asked me, I didn't know, it was in the group chat for a while, and then they're like, maybe he would know. Yeah, it was on Facebook. And they asked me and they said, hey, why is this not true? Why is this not this? And you guys should know it now. What's the difference between x squared on x, which if you simplify it, yes, it does equal to x. Well, what's the difference between these two? You just said it, I think. What did you say, Alicia?
She said it has the and then
it has the okay. It has something. What is different about these two? We would have sketched those two graphs. Why are they different? Okay. Something else. Ben. When x equals 0, remember I said anytime you have a fraction, 0 in the denominator is a problem. So the first one, technically, if you sketch it, yes, it will look like a straight line equation. The only difference is you can't have 0. It's an open circle there. Whereas if you sketch this graph, it will be like that. So what they were asking me was it a mistake when the lecturer said it's x element of R excluding 0, and he was thinking the answer was that. Because he explained to me, he said, that doesn't make sense. Shouldn't it be all real values if you simplify it? And it's true, but it depends on which graph you're talking about. If you're talking about this one, yes, this is correct. If you're talking about that one, that's correct. But you can't say, let's take this and say it's that, because you're omitting one of the conditions. Okay? So that's why it's different. And it's very similar to this one too. 8/4, you simplify it, it becomes x squared, but you remove one of the possibilities or what the conditions are. Okay? All right. Yeah.
So like where you put the brackets won't change what the graph looks like.
But it's what starts off.
Yeah.
Yeah, it's what you start off. So when you simplify it, it does matter. When you simplify it, the conditions change. Yeah. All right. Are we up to the last one? Yep. -4 on 7. Same thing. I would break this up into x4 on 7. It's over 1. As soon as you have a fraction, has asymptotes. Denominator can't be 0. And again, same thing. If the denominator got large, it should have a horizontal asymptote. It should approach 0 on both sides. Because if that gets really large, 1 divided by a very large number, it's very small. Okay? So with that logic, all I know now is the graph has to look like a rectangular hyperbola. The question is, how does that affect anything? Okay? In my case, it's a seventh root problem. Because it's a seventh root, it's technically, another way of looking at it is this. 1 over x to the power of a seventh root to the power 4. It doesn't matter whether it's negative or positive. You can take all values. The condition is okay. You can take positive and negative. You just can't take 0, which we already accounted for. So therefore, to the power 4, I don't care what it is. It just comes out to be a number. Whatever that number is, 1 divided by that is going to give me the shape. It's a number. So you have to think of it as it's just a number. It ends up being a number unless it creates more numbers. Like if I put a quadratic there, that makes a difference. You get 2 vertical asymptotes.
With the second equation, wouldn't that mean that y over is always positive?
Y will always be positive. Yes, could be. That is true. So, that's the second part. So yes, you got your, it's kind of like your 1 on x squared graph. You see, like if I just ignored this, and I told you 1 over x to the power of an even number, you would tell me it's a truncus. True? So, and the reason why is because whatever this number is, doesn't matter if it's negative, you do it to the power of 4, all the negative values go up. Hence you get a symmetrical, so it should look more like a truncus. Okay?
Draw it right in the first place, Simon God.
I was breaking it apart for you.
Sure.
All right, you win. Clearly, you've mastered it.
I don't like that.
I'm a great teacher. So what was the equation again? Negative 4 and 7. So you go, I would eventually. Funny enough, the first class asked about that too. I will one day when I move. But there you go. It is symmetrical.
Symmetrical, yeah.
Can you read my brain?
Sorry?
Can you read my brain?
No.
What am I thinking
That's
right
not
now?
what psych is about.
What am I thinking right now?
Yeah, what am I thinking?
What am I thinking right now?
I think you don't want to do maths. That's probably it.
I mean, no.
Mr. Trent,
Yeah.
I've got a number between 1 and 10. What is it?
What? Look, I'm trying to teach here. When you ask that question,
And I'm trying to learn here, so
what are you trying to learn?
I'm trying to learn if you actually did psychology.
Yeah, you actually have to,
So whether it's true when I say I don't like maths, whether that's true.
I know that's true.
That's pretty obvious.
I
That's
saw
real.
that graph you just put up.
I remember last year you said, I don't want to have any year 12 classes, that's so hard.
It was literally, I was definitely ready not to take any year 12s. Because of last year's group, I was just like, this is a waste of my
It
time.
was semi, wasn't it?
I don't know, I just remember feeling demotivated, going, why am I teaching? I put my effort into this, and they come into class not even ready. I'm like, why do I do this? Year 11s are better. It's just great. You know? They don't care, and I just teach.
Is this class already better? Is this class already better? And if so, who?
Definitely, skill-wise, you guys are much better. Well, I got 2 groups now. Funny enough, I said no, I don't want any, and I end up with 2. Just not even 1, I get 2. So,
Hey, Mr. Tran.
anyways, here we go. Before we waste more time, exercise 1H. Let's go. No, but then the 4th route wouldn't work.
Oh, it's impossible.
All right, year 12's listening. Shh. Last exercise. Let's get going. Applications. It's going to take a while. I want you to have a go at this one. So technically, you don't need me here for exercise 1H. I'm just going through an example just so you see how I do it. When you learnt all the skills, every skill you need is there. I want you to tell me why my hybrid function here is going to be wrong. So let's have a look at, let's read the question here. It says, the cost of a taxi trip in a particular city is $1.75 up to including 1 kilometer. Okay, so that means if you drive from 0 kilometers up to 1 kilometer, between there, it will cost $1.75. Anything beyond 1 kilometer, so after 1K, I will pay 75 cents per kilometer. So that's the problem. Yeah? Now this is what I wrote, and you tell me what's wrong. So I wrote, wait, it's coming up. So 0 to 1 kilometers, so X represents distance that I traveled. It will be $1.75 consistently if I just travel anywhere between 0 to 1. Yeah, so 500 meters, 200 meters, I will pay $1.75. Then after that, I say, well, it's 75 cents. 75 cents per kilometer, so that's true. If it's greater than 1, 75 cents per kilometer. But remember, you have to pay $1.75. Why is this wrong? Sounds right. Looks right. But you graph it. Remember I said everything about methods. If you don't want to make a mistake, try to picture it. What's the mistake here? Ben?
Is it that you included 0 first line?
Exactly that. See, when I have 0, x equals 0, remember, this is after 1. But when I say after 1, technically, that's where 0 is. You know what I mean? So if I sketch it for you right now. Yeah. Because remember, 75 cents after 1. So $1.75 will get me here. That's $1.75. But what I want is after $1.75, I'll be increasing. For every one across, I'm increasing by 0.75. 75 cents up. But that's not true according to what I'm saying here. See, this one actually implies that at 0, that's where I started. At 0, I get, every one across, I go up 0.75. Okay? Does that make sense what I'm saying there? No? Okay. So, if I sketched 1.75 plus 0.75, yeah? This is 1.75, that's a minus it. Plus the gradient, this is what my graph looks like. What I'm saying is, normally, after, let's say, a distance of 0 to 1, I pay $1.75. True? After that, let's say I did 1K above this point. Okay, 1K, that means a total of 2. Yeah, to 1K, that would be 1 times 0.75. But in reality, it's 2. But I haven't accounted for that in this one. You see, when I say 1, when I put 1 here, that means I've traveled 1K plus 75 cents. True? But I've actually traveled 2Ks in total. See what I mean? If I draw the graph, I'll draw it over here so you can see, and it makes more sense. Because what I actually want is this. This is what I want. I want $1.75, 1, and then after that, I want it to be a gradient for every 1, it's 0.75. That's the graph I want. That's effectively what I want. That's what I'm trying to say. The question is, what is the equation for this? Okay, and that's why I'm saying my equation's wrong. So I'll show you. If I sketch this graph now, so we go, oh, actually, I did it prior to this. Okay, wait, is it coming up? Here you go. Have a look at this. See what's wrong with it? That blue section there, that's my 1.75 for 1 kilometer. But the graph that I sketched, 1.75 plus 0.75x started at 0. That's what Ben's saying. But I didn't start at 0. I started at 1. X has to be 1. So this gradient needs to move to the right by 1. Yeah, then it'll be the graph that I want over there. Yeah, that's what I want. See, I didn't start at 0. I started when it's 1 onwards. So therefore, the question is, how do you move the graph to the right by 1? And that's what you learnt last year. Transformations. Moving a graph to the right by 1, you don't plus it. You do plus it in terms of coordinates. You do x, y becomes x plus 1. But when you write it as an equation, it's a minus. Yeah? So normally, remember your quadratics? It was like x squared. If you want to move the graph to the right, you would say x minus 1 squared. Remember that? That tells you it moves to the right by 1. Now it's the same thing for this one. If I want my linear graph to move to the right, that's how I do it. I change that x to an x minus 1, just like you would for last year. I want to move it to the right. That now, you sketch that correctly. If you sketch that type of equation, it will connect at one onwards. Okay? Otherwise, it's currently parallel to it. It's not where I want. I didn't want to start at 0. So it's starting at 1, because that's where my new 0 is. That's where the new 0, 1 is. That's where I count every 75 cents onwards. Okay. Yep.
Oh, actually, you know what? Don't worry. Got it.
Okay, cool. And then once you get the graph right, now you can answer the question. They say find the function f, which I got it correct now. Sketch the graph, then it's correct. Okay. But you see what I'm doing there is just paying attention to little details into the domain. So when you do at the end of year extended response questions, those are the things you got to pay attention to. It's those minor details. They don't tell you. They're called implied domains. You have to look at it, figure out the equation, figure out the domain, sketch the graph, talk about the range, find the maximum, find the minimum, find the distance. That's what extended response is. Okay. Let's have a go with the last one. I think, yeah, we've got 10 minutes. Try this one. Oh, that's the graph of what it should actually look like. I'll put it back. That's what it should look like. So if you fix it correctly, that's how it should look. It should go across and up. Now, let's try this one. I know it's in your textbook. You can look at the answers, but I'm interested in your thinking. Because exercise 1H is about your analytical skills, breaking it apart. What do you have? What do you know? What can you use to figure out the area? Rectangle. Okay, that's your job. Find the area of a rectangle. How do you do this? So you got a rectangle is inscribed in an isosceles triangle, meaning these two are equal. Two angles are equal. With the dimensions as shown, find the area of the rectangle function. So find the area of the shape. Find the area function.
Doesn't make points.
So find the area function and then state its domain. So how do you start this problem? Use what you have. You want to find the area of a rectangle. Write it down. Area is length times width. How do you find length and width? What do you need? Break it apart to problem solving things like puzzles. Given what you have, what can you do to find out your length and width of this rectangle? I give you 4 minutes. Think of it, and I'll show you.
I need that one.
4 minutes, and I'll show you. Meaning that you won't get an area answer because they haven't given you any other information. You'll get a function, meaning like area will equal to x squared. Yeah, so if you know what x is, you know what the area is, but that's a function. So once you know area equals x squared, then you know the domain. And it's isosceles. There's a hint when they tell you it's isosceles. Two minutes left. You can't know by looking at it.
Wait, I need my ruler.
State between like what's the state of the triangle like present? Like
1 minute left.
like 6 plus 15. I would know that.
Alright, time's up. Here we go. Isosceles triangle, break it into halves. Because all you need to know is you need to know the width and height. It's hard to do that, and one of the best ways to do these kind of problems is what we call similar triangles. Back to your sort of year 8, year 9 maths here. If I split it in half, I know that the entire width is 18. So this is 18, but splitting it in half, because it's isosceles, I can say that from here to here has to be 9. That's something I know. So therefore, if I know this is 9, I've got this small rectangle, so I have half this rectangle here. If I know this x and I know this y, I just double it. I'll know the exact dimensions of this rectangle. Okay, so I'm just doing, this is what I'm doing. I'm just saying, what if I half this? I call this x and I call this y. So I ignore this entire right side here. Okay, so I'm just going to ignore that entire right side. What I know is this is 9. I know that I can find the entire height. Now how do I find the entire height? Pythag. So I'm going to use Pythagoras. I'm going to find the entire height. 15 squared minus 9 squared. It's 16. Oh. No, it's not. 3, 5, 4. 12.
Yeah, sorry. Yeah.
Yeah, 12. So, I know that that is 12 now. So now I can write it as a function now. See, I know the area of a rectangle is length by width. I know this is 12, so if I want to know what this is, I can say it's y, call it y. Now, if we're going to use similar triangles, I can use this small triangle here to be equivalent in ratio to this larger triangle. Because they all share the same angle here, 90 degrees, and they all share the same angle here. So I can use similar triangle to solve this out. Okay, so I'll draw it here so it's in the video. So in the video, what I'm trying to say is, if this is y, I can find out this height and this length, and this is a small triangle. In comparison to a larger triangle, which I'll draw in blue, this is my larger triangle. Okay, so if I highlight it now, I'll do another highlight. I'm just saying, this entire large triangle, I can use similar triangles to compare it with. I'll do in green, so you can see with this triangle. Okay, now I called this x, and I need to find out what this length is. Okay, so you can see, if I call this x, I know the entire length is 12. I know from here to here is y. And this leftover side must be 12 minus y. Agree? Okay, so I'm just saying this is now 12 minus y. Reason why I do that. So you draw it out. The green triangle which I'm drawing here. I call this X. I call this 12 minus Y. I'm comparing that to a larger triangle where I know this is 9 and that is 12. Similar triangles. These two are equal to each other. These two are equal to each other. Times both sides, cross multiplication. Rearrange. And you get this function. But remember, you're trying to find the area of rectangle. 2 times x times y. Sub everything back in. So you got y already. Sub it in. Have a look at the PowerPoint if you want to look at it again. And that's how you do this problem. So the hardest part is the start. Okay? Thank you very much. That's 1H tomorrow. Get an assignment to get time to do 1H as well. Cheers up, please. Cheers up before you go. Cheers up before you go.